Hi, I'm Ketki Mehta and I will be presenting thermal comfort in hot and semi-arid climates. The research is done in three parts: assessment of outdoor thermal comfort, bioclimatic building envelope for indoor thermal comfort, and thermal adaptation. We present here design tools for assessment of outdoor thermal comfort. Field studies show variation from outdoor thermal comfort standards. INMET has produced for Brazil a chart which takes this into account. Algae's bioclimatic chart can be modified for lower latitudes, in this case 9 degrees south. Juxtaposing these two charts gives a resulting chart which is ready to be used. The CLO in this case is 0.5 and MET is 1.3. So depending on the activity, it needs to be corrected. Here's an example of how it could be corrected for classroom and gym. This is done monthly by plotting daily temperatures, and a summary of this is shown here. You can see how some parts of the day for each month are really hot for the gym, and some parts of the day are very useful for the classroom activity. In addition to this, land surface temperatures become very important in outdoor thermal comfort because 43 degrees is the maximum temperature that the human skin can bear. Side wind is also important because wind temperatures can increase heat discomfort, and wind speed can help reduce discomfort. Site shading can be studied in detail because different areas of the site have different shade at different times of the day and different times of the year. 35 shading masks were juxtaposed, each one of them with a mirrored solar chart to create a site grid showing the probability of shade in each part of the site for each hour of the day. Proposals were made using all these studies, and they were tested again with the shading masks and CFD for wind. In conclusion, there's 4 parts to assessing thermal comfort for outdoors. First is field studies. Second is Algae's bioclimatic chart, rectified for the latitude, for MET and CLO calculations. And the fourth is evaluation of wind, shade, and land surface temperatures. The second part is indoor thermal comfort, which was undertaken using Kubota method. This is a method that was arrived at by them using meta-analysis of the RRP84 database. They arrived with separate equations for hot, dry, and other climates. The preferred temperature was 3.5 degrees below neutrality for hot and dry climates, and the upper limit was 2 degrees above and lower limit 6 degrees below. And they found that the higher wind speeds did not change neutrality for hot, dry climates. This is a summary, a snapshot of their equations. An iterative process was followed by first making a base case in Design Builder and then testing it for 3 cases for each parameter: occupancy, U values, WWR, windows, and thermal mass. The results of these studies were further tested for these 6 elements: porous wall, natural ventilation, cross ventilation, thermal mass, roof as a solar barrier, self-shading windows, light permitting, solar blocking windows. And these results were taken and the best cases combined to arrive at an optimum case. As you can see, the results were collated for wind speed, wind temperature, daylighting, operative temperatures, RH, air changes, and the resulting Kubota annual hours were looked at, and daylighting factors and other indices were also looked at. These results were analyzed in a chart like this, showing which components were higher and which results were better. What the results showed is that high thermal mass with low U value, big windows shaded carefully in the right direction, porous wall, cross ventilation, and most importantly, a double roof which acted as a solar reservoir were very useful components for a highly effective bioclimatic building envelope. These charts show indoor wind speed, wind temperature, operative temperatures, annual hours for thermal comfort, and annual hours for daylighting across the simulations. In conclusion, the Kubota equations present a very realistic picture of thermal comfort in hot and semi-arid climates. Low U value and low wall-window ratio, in itself do not guarantee thermal comfort. In fact, by only keeping low U value and low WWR, you are limiting what you can do with the bioclimatic building envelope. Thermal adaptation is the part 3, and it can be a predictor of thermal comfort. Thermal preferences from different bioclimates show that the lowest thermal neutral temperature is 10.7 degrees and the highest is 29.23 degrees, which is quite a range. Two types of adaptations occur in the human body. One is heat adaptation and cold adaptation. The cold adaptation always results in thermogenesis, higher metabolic rate, which means you have more brown adipose tissue, higher body mass, higher basal metabolic rate. The heat acclimatization results in greater sweating, so lower sweating threshold, lower body mass, and better water balance. And these are important in increasing cold tolerance and heat tolerance, respectively. Neurophysiologically, what thermoreceptors do is within a certain range, they affect certain actions within the human body, and these depend on the kind of adaptation or the level of adaptation that your body has. So less than 5 degrees or greater than 43 degrees is usually very difficult for most people to be comfortable. Between 5 and 15, if you're adapted to that temperature, with the right kind of clothing and a well-insulated house, you would find yourself thermal neutral, like in Nepal. If you are in 15 and 26 degrees, in that range, it's temperate weather, and if you are adapted to the cold, you would find it very comfortable. But otherwise, you might find it a little cool and need an extra layer. From 26 degrees to 32 degrees, if you're adapted to the heat, you would find it comfortable, although you might prefer a slightly lower temperature. But if you are not, it would cause you heat stress. From 32 degrees to 43 degrees, only those who are adapted to very high heat would find it bearable and be able to be okay without falling sick. So these ranges and the kind of response your body has shows the importance of the level of adaptation. This graph is a summary of the thermal comfort ranges for people adapted to temperate climates, hot humid climates, and hot dry climates. In conclusion, thermal ranges are based on neurophysiology that should be taken into account. Comfort varies depending on your level of acclimatization, and this level can be ascertained using certain tests. For future research, adaptive bioclimatic charts for different locations, especially for outdoor thermal comfort, should be created. Kubota equations need to be further validated by field studies. More components for bioclimatic building envelope need to be researched for hot semi-arid climates, and field studies which tell us about how level of acclimatization affects thermal comfort would be very useful. Thank you for listening. And thank you so much for being such a great audience. You can connect with us on LinkedIn. Thank you.